Hello, my name is Dennis Derrickson. I'm a professor at California Polytechnic State University, and I'm with the Electrical Engineering Department. Today, I'm going to continue in the series of noise videos I've created, and this time I'm going to look at a black box noise model for a gain block, trying to simplify the noise coverage from the transistor and resistor and diode level coverage we had previously in previous videos. So I'll quick give an overview of thermal noise and shot noise in an amplifier, and that is kind of a complicated analysis. And so I'm going to introduce a black box model where we're going to simplify the noise modeling, and we'll create parameters like noise figure and noise temperature and gain of an amplifier, but not have all the individual transistors called out. Then we'll look at cascading black box amplifiers in a range of one or two or three or four amplifiers. And then we'll introduce a particular black box amplifier, which we'll do experiments with, which is going to be the mini circuits ERA 3 plus gain block chip. Then we'll do some measurements of the gain of that chip, and then we'll create a noise model for that, a black box noise model, and we'll measure that with a SSA-X from Keysight, looking at the baseband noise and the broadband noise, and see how that might compare with our theory. Okay, so let's get started with our black box modeling of gain blocks. Now, previously we had gone through an example looking at a simple transistor amplifier. In this case, it was a 2N2222 bipolar junction transistor. And we had this simple circuit right here, a common emitter amplifier. Now, to analyze that, we had to take the 2N2222 transistor, figure out its DC operating condition, come up with a circuit model for the transistor, and then place noise sources in strategic locations for that model. On the right-hand side, I show the model for the single stage amplifier. On the base, I have a physical resistor that's with the base connection, and it produces thermal noise. And so I have a source here. In this case, it's a 12 picoamp thermal noise generator at the input of the amplifier, caused by the low doping in the P region. Then I have a dynamic resistance right here that represents the change in voltage over the change in current of the base emitter diode, and it has shot noise. And so I have a 4 picoamp shot noise source with the base emitter diode. And then the base collector diode also has shot noise. And so I've calculated both a 4 picoamp shot noise on the base emitter junction and a 56 picoamp shot noise on the base collector junction. And then I have to propagate all those noise sources individually to the output, compare them, and finally I can figure out what kind of noise we have at the output of this amplifier. So it's an involved process, but it does give you a lot of intuition about what's happening inside the transistor. So I'm going to introduce a way of taking these detailed models and just putting in a big black box where we're not worried about individual transistors and resistors, and we're just going to have a black box characterization of that gain and noise that's associated with the amplifier. Okay, so here is going to be my black box model for any gain stage. At the left-hand side, we have a source, which is going to stimulate the amplifier in this case, and we're going to say the amplifier is just going to have some input resistance right here, and we're going to assume it's real, and we're going to call it Rn. And then we're going to have a dependent voltage source that says that this voltage is some voltage gain AV times the input voltage. And then the black box has an output resistance, and that will drive the load. So, the most basic model of an amplifier, we're going to call this a black box gain stage. So this model takes care of the gain characteristics and the input and output impedances, but it doesn't take care of noise. So let's take this black box model and add noise sources to model that behavior of the noise performance of the amplifier. Okay, so this is a little more complicated right here. So right here is the black box model. But I've added two more things right here. I have a current source here and a current source here. And those two current sources are going to model all the noise for all the transistors and resistors inside this circuit. And we're going to pretend it's not true that all these noise sources are associated with the input resistor right here. And the output resistor, we're going to assume has no noise at all. And we're going to lump every noise source inside this black box as if it were attributed to this input resistance right here. And we're also going to take a model that makes it look like a thermal noise. Even though we have shot noise, 1/f noise, we're going to say that Rn is our noisy input resistor, and it will have its own native thermal noise. And so that first current source right here is just a native thermal noise of that input resistance. So here's a thermal noise equation, the square root of 4 times K times the actual temperature of that resistor times the bandwidth of the observation in the system divided by the input impedance. And so that's going to be a traditional just thermal noise associated with that resistor. Now we're going to also then add another noise source, and we're going to call it the excess noise source. And we'll have the same formula form as thermal noise, but we're going to create this new factor called the excess noise temperature. Now, the excess noise temperature does not represent a real temperature like you'd measure with the thermometer. It's just a fictitious number, and we adjust its value to make sure that if we lump all noise sources as if they were created at the input, that number will create the right amount of noise at the input. And then, of course, at the output, we'll amplify this input noise to get the output noise into the load. So all the thermal noise, shot noise, 1/f noise from the transistors, diode, resistors, all will be lumped into this single constant called the excess temperature. And that will be frequency dependent. The excess temperature will be different at different frequencies. But that is a single number that's going to kind of model the noise performance of this amplifier. Now, there's some related quantities to the thermal noise temperature and the excess noise temperature, and they're shown below here. We're going to define something called the amplifier noise factor. And the noise factor is going to be defined as 1 plus the excess noise temperature, which is fictitious, divided by the actual noise temperature. So if we had the excess noise temperature and actual noise temperature being the same, then we'd have a ratio of 1, and we'd say we have a noise factor of 2. Oftentimes, we want to do this in decibels, and so the noise factor is going to be, should be 10 log of F. I have 20 right here, but noise factor right here. So oftentimes in radio astronomy, they'll use the excess noise temperature. In many data sheets for RF microwave, we'll oftentimes use the noise factor and noise figure. So we have a situation right here shown on the right that the output voltage on this thing right here is going to be the input voltage times some voltage gain. That's the signal. And then we're going to have all the noise of the amplifier associated with Rn. So we're going to take this total noise current right here times Rn. That will give you the effective input noise. And we'll multiply by AV to get the output noise. And so this is a black box model of a gain block, simplified so we don't have to deal with all the individual transistor noise elements. So this is very useful for making cascades too. So let's look at a really interesting diagram that's oftentimes used in systems engineering for RF and microwaves. And that is to having black box models that are cascaded and being able to figure out what happens from input to output with this cascade. So here we're going to start, on this axis we have two variables. One is the signal power, which in this case is 40 dBm at the source, minus 40 dBm. And we'll have noise power, and we're going to have it in units of decibels compared to a milliwatt and in a 1 hertz normalized bandwidth. So at the input right here, we're going to assume these are all 50 ohm sources for this exercise. And so we have a signal right here at minus 40 dBm. And the noise power associated with this resistor here is thermal noise at minus 174 dBm per hertz. So it's minus 174 dBm per hertz. And then we have our first gain stage right here. We have thermal noise of this input resistor, and then we have excess noise of this resistor. This particular one, we're going to assume it has a noise figure of 3 dB, which means that the noise factor is 2. The excess noise temperature and the actual temperature are the same. And we're going to assume it has a gain of 20 decibels from input to output. So then we start looking at what's happening to signal to noise at the input of this amplifier here. So this area right here is associated with this area on the noise versus position drawing below. So we have minus 174 dBm per hertz from the source right here. We have another minus 174 dBm per hertz, and we're going to add them up to get minus 141, because if you have two equal powers, then if you take 10 log of two equal powers, you get a 3 dB rise. So we get minus 171 dBm per hertz, total noise across Rn. The signal is at minus 40 dBm, so the signal to noise ratio is minus 174 minus 40 dB, so we get 141 dB signal to noise ratio. SNR is signal to noise ratio. Then we're going to say this amplifier will amplify both the signal and the noise. So the signal starts at minus 40. At the output of the amplifier, it will go to minus 20 dBm, since this is a 20 dB gain amplifier. The amplifier will amplify the signal, but it will also amplify the noise. And so the minus 141 dBm effective input noise will be amplified by 20 dB to get minus 141 dBm per hertz noise level. And if you take the difference in dB between those two, you get 141 decibel signal to noise ratio. So we've lost 3 dB of signal noise ratio from the input to the output of this first stage right here. Now, the second stage has the same two noise sources, the same amplifier, so we're going to get minus 174 dBm per hertz in the thermal noise. The excess noise is the same. We're going to double it by 3 dB increasing, and that gives you minus 171 dBm per hertz. But the amplified noise from the first stage is minus 151. And so the amplified noise from the first stage is so much larger than the thermal noise at the input of the second stage that you could ignore it. Makes no difference. So the noise figure of the second stage made no difference and made no contribution to the overall signal noise ratio. And then finally, we're going to amplify the signal one more time, going from minus 20 dBm to 0 dBm. And the noise is also amplified, going from minus 141 dBm to minus 151 dBm to minus 131 dBm. The noise has the same gain as the signal. And at the end, we have, again, this load, which has its own thermal noise, but it's so low that it doesn't matter because the amplified noise from the previous stages are so much greater. And at the end, we still have 141 dB signal to noise ratio. So in these cascades, one thing that you learn is the most important thing in preserving signal to noise ratio is to have your first stage of amplification as low of noise as possible, because the second stage's noise input probably doesn't make too much of a difference if the first stage of gain is large enough. So this is a cascading of black boxes, looking how the signal propagates through, looking how the noise propagates through from input to output. Let's go through an actual example here. So I'm going to use a mini circuits ERA 3+ gain block, and here's a picture of it. This is something that the students have put together at Cal Poly. Here's the actual ERA 3+ gain block. We have an input SMA connector, a DC blocking capacitor here, another DC blocking capacitor. And then we have our bias coming in right here at 10 volts. The amplifier schematic is shown here. This is what's called a shunt feedback, meaning that the output of this amplifier is sampled in shunt and fed back to the input in shunt. So it's a shunt feedback. And it's designed such that the input impedance is 50 ohms and the output impedance is 50 ohms. And this circuit on the upper right here is just implementing the recommended circuit that was shown in the data sheet for the ERE3 Plus. And we use a 10-volt bias and a 191 ohm resistor right here. And we have an RF choke. There's the RF choke right there. RF choke is just a high impedance inductor that doesn't have too many resonances. Let's look at a little more on the data sheet. Some key parameters are the gain of this amplifier is around 20-ish dB, depending on the frequency, low 20s. They're closely matched to 50 ohm input impedance here. There's the input return loss, so that means it's really close to 50 ohms input and output impedance. You can put out about 12 dBm of power. At 1 dB compression, 3 dB compression point is 13 dBm. And here's something I wanted to show you here, that the noise figure over a broad range of frequencies is around 3 dB. So this is very similar to the description right here on these blocks of gain of 20 dB and noise figure of 3 dB, and that was intentional. Okay, so let's do some measurements and see how our black box theory works. So we're going to use this ERE3 Plus gain modules. Here's two ERE3 Plus gain modules. They're cascaded. I bring in DC power right here, 10 volts, and then I have connections to my vector network analyzer right here to measure gain. I have connections to my spectrum analyzer right here to measure spectrum power over a 0 to 54 gigahertz frequency range. And then I have this really sensitive baseband receiver that can go from 10 millihertz to 10 megahertz. And I'll do measurements of all three of these right here to show how the black box model works. Okay, let's do a first measurement. Let's measure gain of these amplifiers, both single stage and cascaded stage of the amplifiers. We said they're about 20 dB gain each. Let's go take a look. Okay, so here is a single ERE3 Plus amplifier biased at 10 volts. There's a little chip, and we measure gain versus frequency. In this case, I went from 100 kilohertz to 5 gigahertz. And I've sampled a couple of points here, 10 megahertz, 100 megahertz, and 1 gigahertz, and brought out some gain values right here. So, you know, a little bit more than 20 dB of gain for a single stage. And I put in minus 25 dBm of input power so I don't hit saturation. When I put two of them as cascade, I brought the power down a little bit to minus 35 dBm. So I wanted to make sure I didn't go into a saturated case for this amplifier. And for two stages, I get double the gain in dB. So at low frequencies, I'm getting about 43 dB gain. And similar at 1 gigahertz, we have a little bit over 40 dB gain. And because this is a cascade, the input noise figure is 3 dB. The input noise figure for the second is 3 dB, but for the cascade, total cascade noise figure is still going to be around 3 dB because the amplified noise of the first stage exceeds the effective input noise of the second stage. Now, I want to look at the noise performance, and I'm going to look at the baseband input. And this is a really sensitive correlation receiver that measures from millihertz up to 10 megahertz. And so I'm looking at this amplifier. This amplifier has its gain roll off at around 100 kilohertz due to the AC blocking capacitors. Here, this is the AC blocking capacitor there, AC blocking capacitor there. It acts as a high-pass filter, drops the gain at low frequencies. But above the high-pass corner, the system puts out a noise of about, for a single cascade here of about minus 161 dB volts per hertz. That's the noise level we're measuring. So let's see if that makes any sense. So we have here an attenuator, and that attenuator is 50 ohms, and it should have a minus 174 dBm per hertz noise floor. But we're measuring in dB volts at this input, so the equivalent dB volts for thermal noise from a 50 ohm resistor is minus 181 dB volts per hertz. But then we have the 3 dB noise figure of the amplifier, so I'm going to add 3 dB. And then we have about 22 dB gain of this amplifier right here. So I should get around minus 156 dB volts per hertz, according to my calculation. So I throw it on the baseband input of the SSA-X, and here I get a measured noise level of about minus 161 dB volts per hertz. So not exactly the same number. I haven't analyzed why you get the discrepancy, but they're similar numbers for the output noise from a single stage. Then let's look at a cascade of 2 amplifiers. I still have my 50 ohm input right here going through one 22 dB gain amplifier, another 22 dB gain amplifier. And so I measure the output noise above the high pass corner frequency of about minus 140 dB volts per hertz. So what should we expect based on the model? So we have thermal noise in the resistor here at minus 181 dB volts per hertz. Then I add the 3 dB noise figure of that first stage. And then I add 43 dB gain for the 2 cascades. I get minus 135 dB volts per hertz. And we're measuring minus 139 dB volts per hertz. So a few dB off, but that's my measurement of the output noise with this correlation receiver that's very sensitive. Well, let's look at the broader frequency range. So the spectrum analyzer, typically these wide bandwidth spectrum analyzers don't have the sensitivity that the 10 megahertz correlation receiver has. So I have 2 measurements right here. One is this is a single stage of this ERA3 plus going into the spectrum analyzer mode of the SSA-X. And that is this plot right here. That's the output noise right here at minus 94 dBm per hertz, something like that. I also just terminated the input right here without the amplifier to see what the noise floor is right here. So this is about the floor of the measurement instrument with the spectrum analyzer terminated in a 50 ohm resistor. So I have only a small amount of signal noise ratio here, like 3 dB signal noise ratio, maybe 4. My theory says I should measure here minus 174 dBm per hertz. That's the thermal noise level for a 50 ohm resistor into a 50 ohm load. I have a 3 dB noise figure plus 22 dB gain. And I need to denormalize this into a 1 hertz bandwidth. Since we have 100 gigahertz as a resolution bandwidth, that's the width of the filter of the spectrum analyzer ahead of its power meter. I have to take 10 to the 5th, 10 log of that, it's 50 dB. And so it says I should get minus 99 dBm in a 100 kilohertz bandwidth. And so I measure here with this measurement at minus 94 dBm at this level right here. So I think that this is a little close to the noise floor. So, you know, if they're equal contribution, they would drop by 3 dB. So I think that brings it a little closer right here. So it's reasonably close, especially when you consider that the noise floor of the instrument is so close. Let's go look at the cascade of 2 amplifiers with the spectrum analyzer. So now we have 2 of these amplifiers in cascades. We have lots and lots of gain. So the noise is just spewing out of this 2 amplifier cascade. We have the 50 ohm termination. We have amplification of noise here, more amplification of noise. So here the noise is much larger. Also, I might point out right here that in this environment right here, I'm actually picking up a lot of internal signals at my site here at Keysight. So this is probably a bunch of Wi-Fi signals that are being picked up by these amplifiers and aren't well shielded. We've got some other frequencies. So lots of pickup here being amplified in our ERA3 plus amplifiers. But the baseband, the general noise is this level right here. If we didn't have all these spurious signals we're picking up from the RF environment here in the lab. We should see, starting out here, thermal noise minus 174 dBm per hertz, add 3 dB noise figure, add 43 dB of gain for 2 of these, plus 50 dB to denormalize 100 kilohertz resolution bandwidth down to 1 hertz. And I should get minus 78 dBm in a 0.1 megahertz bandwidth. And so my marker here says minus 77 dBm noise. So that's a reasonably close number to our prediction versus what we measured right here. So let's do a summary of what we kind of learned right here. I started out with saying that in an amplifier, there's many transistors with shot noise and thermal noise, and it gets complicated to model noise at the individual component level. So we're going to create this black box where we just have the amplifier modeled with some input resistance, some output resistance, some voltage gain. And we add these two noise sources right here. The first noise source is going to be just the thermal noise of this input resistor right here. And here's the thermal noise formula right here. And that would be like minus 174 dBm per hertz for the input resistance. Then I'm going to add a second source right here called the excess noise temperature and the excess noise source. And that single value TXS is going to model every noise mechanism besides the thermal noise of that. It's an experimental parameter, and it's not a real temperature. It's a fictitious temperature. You can have excess temperatures of thousands degree Kelvin, but that's not how hot the amplifier is. And so then we can create two versions of that, the amplifier noise factor, which is 1 over T excess over T actual, and then we can also take the log of that to get the amplifier noise figure, which is a decibel figure. So I hope we had an interesting time here looking at simplifying noise models. And next we're going to do is we're going to look at how these amplifiers can degrade the performance of an oscillator if you cascade an amplifier after an oscillator.